All right, this is first part of a multi-part presentation focused on calculating the percent crystallinity of a polymer. And in this first one, I just want to help make some sense of the formula. And so we're kind of just presented with a formula for the percent crystallinity that has this form. It's equal to the density of the crystalline polymer divided by the density of the sample times the density of the sample minus the density of the amorphous polymer divided by the this value. All right. So where does this formula come from and why are we using it? And this formula, by the way, has to be multiplied by 100. We can also talk about the fraction of crystallinity. In that case, we would not need the 100. The 100 goes away. All right, so where does this formula come from? If I were to make a plot of the density of these various polymers that we're talking about versus, then I'm going to call this fraction of crystallinity. All right, where if we define kind of, and I put 0 in quotes and 1 in quotes. So if we imagine that we have a fully, quote unquote, amorphous polymer lacking any crystallinity. And so when it has this state, we say that it has no crystallinity. And so the density of that state, we label that the density subscript A for amorphous. And similarly, for a fully crystalline, so this would be non-crystalline or amorphous, lacking shape. So when the fraction crystallinity is 1, we would say it's fully, quote unquote, crystalline. And so at this fully crystalline state, this polymer will have a density that we will label density subscript C for crystalline. And so if I add those 2 points to the plot, what is true is that there's a linear relationship between these two as we increase the fraction crystallinity of the material. Another way of saying that is if I have if I pick a point on the curve and I label that the density of a sample, S for sample, this would be something we don't know. So this axis up here is density. It has units of grams per centimeter cubed. And so this density of a sample would correspond to a fraction crystallinity that I could call here, C, let me just call it CS. So that would be the crystallinity of the sample. And so what this formula is telling us, and I'm going to write it a little differently because it makes sense to me in my head to think of it this way. So what this formula is telling us is that the difference between the density of the sample and the density of the amorphous phase, so I'm going to call that difference delta 1. So it's telling us that that delta 1 divided by its that density, so if we kind of choose the upper point as a comparison point, so delta 1 divided by delta S is a value, and that if we compare that value to a second delta, which is the total difference between the crystalline and the solid, so if we compare that to that second difference, which also then gets kind of compared or ratioed by the density of the solid as a reference point. So that this is the fraction crystallinity. And we could turn it into percent crystallinity by multiplying both sides by 100. And I'm going to just take a moment to write this out a little more formally. So in a full-on formula, what this is saying is that the density, so I'm just going to, this is the density of the sample minus the density of the amorphous phase divided by the density of the sample divided by the density of the crystalline phase minus the density of the amorphous phase divided by the density of the crystalline phase. So if we flip this over and do a little of gymnastics to it, what you will see is that we end up with exactly that formula, that this is why you have this crystalline density on the top and the sample density on the bottom of the liters. And then again, these other two factors are differences of the densities. And so I like thinking about the formula in this lower way, and you're going to see me use this formula that I'm going to label fraction crystallinity as I continue to solve these problems, just simply because it makes some physical sense to me. All right, that's it.